Good morning, everyone. Hi. I'm Chiba from IBM Research. Here's Takuya Mishina. He is also IBM Research Tokyo. Yeah, today we are excited to share our great stories and journeys, and also the lessons learned how to enable the IBM AIU Accelerators in the Kubernetes. So, all right. So let's get started. So this is a straight line what we would like to share today. So just want to share, like to share first the AIU accelerators. That's a brief. I would like to just briefly introduce that. And also we are so many journeys, lessons learned how to enable, but we have making some primary design on enabling AI accelerators in Kubernetes, but we have so many rounds from that, and we also changes some design and using the custom schedulers or some, including some extended custom resource distributions to keep in a state as possible, right? So then we also set on some say about touching on a little bit about the DRA, the coming next functionalities we are providing soon. Okay, so. Okay, this is today's highlight key 3 things I'd like to mention here today. So, so I cannot cover everything in this short period of 30 minutes talk. So, but well, so first things is a limitation of a sophisticated allocation at the device plugin. We can deal with that. Right now, it's using the DRA some part, but we have struggling for the a kind of the fine-grained, sophisticated allocations in the previous device plugin. So that is how we can deal, how to overcome that limitation using the schedulers at the device plugin. The second topic is the topology. So this is relatively interesting for the community, I think. So we are using the hardware lock LSPCI-based library to get in there some list of the hardware devices in the host, but it sometimes is not correct or not sufficient to run in some workloads. So we have to take care of the topologies as much as possible, even for the in the device in the accelerators topologies, right? So the third thing is mutating webhook. So we have providing the mutating webhook on the account of the issues. So some people do not familiar with Kubernetes. We have to teach or how to navigate user to use a correct YAML file sometimes. So that is we are preparing. But we have to touch on a little bit about how to manage this mutative webhook versus the validation webhook. So that is the key things for that I'd like to share today. So some other features like no feature discoveries, labelings, or module dependencies, vulnerability management, and we have so many solving the Go module dependencies, and also we have to, previously we had changed some names, just AIU, but we have to change from AIU to Spire. So in that sense, we have to take care of so many changes within the repository. So those are stuff with the Rust and run, especially for the renaming. So other things not sharing here is we are developing QEMUs on the device, mock device to simulate and emulate the behavior of the devices without any actual code. So those are kind of stuff we are doing to keep developing all the functionalities and to timely release our operator to the community. So, all right, so that's let's see. So let's go now next. So that is a brief background of the growing demand in training and inference, right? So it's now is a decade of the innovation of the LLMs. Always applying the general AI, RDMA agents, robotics, material science, and the drug discovery. Those are we trying to apply LLM to the enterprise field, right? So as you know, we are now increasing the AI costs. Okay, so AI models is getting both larger and smaller, right? So we have developed in the frontier models, 400 billion scale model, but at the same time, we need to make a more smaller model to adapt it to the not only data centers, but also edge, right? Those kind of the both larger and smaller is coexist in the AI model. Okay, so training is very tough, right? But it's also many spend more time for the infrastructure cost and electric power. We have a so huge demand for the reducing the power itself, right? So that's some background. We have to some opportunities or motivation to make a purpose-built AI accelerators. So now it's the AI accelerators, purpose-built AI accelerator is now becoming more and more popular, right? Not only in GPUs, GPUs, Intel Gaudis, AWS training inferential, Google TPUs. So, and then we have our IBM Spire. So that's the stories of the background. Okay. This is IBM AI Spire. We recently announced this new capability of the AI accelerator. PCI card is designed to handle the AI inference and generate AI as efficiency as possible. Okay. The Spire card itself is a 70 watt, 5 watt, and can install in the PCI Express card. That means we can set up this card into the, according to the number of the PCI devices slot on the board, right? So that means 4, 2, 4, 6, 8, 12, whatever. So this is bring the topology matters, right? So that's need to consider as much as topologies as more and more. Okay, so let me just give some example why we need to take care of the topology aware more. So we defined 3 scenarios for the topology awareness. Okay, scenario one, I want to run single workload on 2 Spire devices. Okay, but in some cases, we'd like to allocate devices under the same PCI switch in some reason or communication, whatever. So those are kind of stuff. Scenario one, we want to collocate Spire accelerator card as much as possible in the same PCI devices. It's PCI 3, sorry, PCI root complex. If we want to expand the workloads to multiple nodes, we want to collocate NIC as much as possible, right? So in some cases, we want to consider over not only devices, but also the considering collocate with the NIC devices, virtual NIC, or some physical NIC and whatever. So that is a scenario 2. Scenario 3 is almost same for the NIC use cases, but we'd like to keep using the same NV switch that exists in the same PCI switch. Okay, so in terms of the copying data, NVMe to the devices, directory for the key cache store or checkpointing, anything. So those are allocation devices, co-location with a defined, the enemy device is also important. So that's why we were considering all the topology architecture structures and then carefully to consider what optimal topology, optimal scheduling. Okay. Okay, so I'd like to hand it over some of the rest of the part of the primary design, how we can deal with that and how we can enable and making sure to explain some lessons around.
Hi, this is Takuya. I'm working with Tatsuhiro at the IBM Research Tokyo. Let me talk about, from now on, let me talk about the first primary design of our enablement for the AI accelerator in Kubernetes. Okay, so let me first describe how the Kubernetes manages the devices. So on each node, there's a kubelet running on the node, and then Kubernetes is responsible to manage its devices, but the device-specific operations like initialization will be delegated to its own device plugin. For example, if there are GPUs, then the GPU device plugin is responsible, for example, to initialize or some preparation method. And we implemented the device plugin for Spire. And as just Tatsuhiro mentioned, we have several use patterns, and it derives several slice patterns due to the topology awareness. So So there are many Spire devices, but they can play various roles in the workload. So we may use these pairs or these pairs, like so on. So we want to allocate the appropriate sets of devices. Okay, so in that case, as we talk, there are several scenarios. But our challenge here is that the device plugin cannot accept any parameters as for now. So this is the standard manifest to request some device. As you can see, the only thing we can specify is name and quantity. So we wish we could say some policy. For example, I want 2 Spire cards, but they should be under the same PCI switch. So tier 0 means the same tier on the PCI switch. But it is not feasible in the current device plugin mechanism. So how to solve that? So our solution is that the populating request type as resource name. So, okay, we cannot use anything rather than resource name and quantity. Okay, then let's encapsulate parameters into the resource name. So, for example, not just /Spire, but also /Spire, for example, tier 1 or /Spire dev something. So we can specify a certain PCI device to assign the card to the pod. So this is our solution for no parameter, but it incurs another issues. So let's consider some example. So, okay, in the initial situation, we have 2 remaining devices, and user, okay, let's assume that user requests 2 Spire devices. Then, 2 tier 0 devices. Okay, these dev21 and dev22 are under the same PCI switch, so the request can be achieved. So the number of remaining devices from 2 to 0. But please note that the Spire and Spire tier 1, both of the resource name refer same device. So we should synchronize the number of remaining devices. So if the tier 1 becomes 0, then the Spire also became 0. So device plugin must populate real allocatable number instead of the virtual number. So when the allocation happens, then the device plugin must explicitly synchronize the remaining number of devices. Okay, so that is our first idea. And the second one is the usability support. As Tatsuhiro mentioned, we provide AI Accelerator in Kubernetes, but not all of the AI workload owners are familiar with Kubernetes. So we provide some, syntax sugar for them. So this is the example of such a support. For example, if user just write a label, then it will be expanded into some sidecar containers. So no need to specify concrete name of image name for the sidecar container, like so on. And if user forgot to add required specs, then the mutating webhook add the missing specs to the manifest. Okay, that's the primary design, and here let me share the lessons learned found in the primary design and its implementation. Okay, the first one is a limitation of the sophisticated allocation at device plugin. So as I mentioned in the previous slide, we introduced a multi-resource name solution with explicit remaining device number synchronization. But the time lag of the synchronization exists between device plugin and the kubelet or its device manager. So such a small time lag may cause for example, duplicated allocations, especially at the time of burst request. So when user throws many requests at a time, then it triggers duplicated allocation data issue. And another challenge is that the default scheduler does not consider topology or the resource and the utilization. So let me use another example. So here, there are two nodes. One has two remaining devices, which are tier 0 relationship, and another node has two devices, but they are not a tier 1 relationship. In this case, let's assume that user requests the simple two cards. Then, in this case, we want to preserve these devices for future requests, future tier 0 requests. So when users request two simple Sphere, we want to use this node for that workload. But the default scheduler does not care such a topology, as it just considers the number or quantity of the remaining devices in a node. That's why we cannot optimize over the multiple nodes. And another lesson learned is that the topology generation. So we have a library which is called HWLog, hardware log package, so which provides information about the PCI devices. So we can see the tree of the devices. And yeah, this is the example case of the 1, 2, 3, 4, 8 IBM devices under the PCI bus. And here, this is the simple output, but in the background, there is some hidden truth. For example, if the device, the node is virtualized, then it doesn't provide the actual, the hardware information to the upper side of the program. For example, the issuer of LSPCI command. So therefore, we should deeply investigate the situation of PCI devices, not just depends on the existing library. And third lesson learned is mutating with webhook. So again, so it's stability issues against the burst request. So mutating webhook is very useful for the end users to automatically configure or fix the manifest, but it changes the manifest, which occasionally introduces the some inconsistent situation. And another issue is that it's difficult to support all possible workload types. So what does it mean? So mutating webhook has its configuration, and the configuration contains what is the target resource of the mutating webhook. So we first focused on the core APIs like pod, deployment, and job. That's okay. But in reality, there are many custom resource types in the AI workload management system. As someone said in the keynote speech, there's a K-sub, or another example is Kubeflow. They use their own custom resource to manage their AI workload. For example, PyTorch job in Kubeflow or inference service in K-sub. In that case, our hook can be applied to the derived resources. For example, inference service creates a deployment, and deployment creates pods. So in that case, our webhook can apply such a derived core API resource, but we can't directly check the custom resources. To do so, we have to add a special logic for that custom resources. So we decided to use the validating webhook instead of mutating webhooks to make a more stable environment. Okay, from now, let me introduce the improved design based on our lessons learned. So we introduced a custom scheduler instead of the default scheduler, and it has a reservation capability. So why we introduced the custom scheduler? There are two reasons. One is the topology-aware node selection, as I mentioned previous slides. It can bind pod to a best node regarding device topology, as I shown in this example. So the custom scheduler can consider which is the best node with respect to topology. And the second idea is device reservation. So the custom scheduler reserves devices prior to the allocation in the device plugin. So custom scheduler writes the reservation result to a custom resource, and then device plugin allocates the reserved devices, so which it can prevent the inconsistent allocation or duplicated allocation. So we can sort of the lock object for the devices. So we can use the reservation entry as a lock object. Okay, this is the process to allocate the device to a workload, pod. So at first, a custom scheduler checks the custom resource, which is called node state. It contains the not only contains the AI device situation, but also topology and allocation status or reservation status. So the scheduler can select available devices from this custom resource and write the reservation here, and then bind the pod to a certain node. Then the device plugin on the node read the reservation status and then use it and allocate the reserved device to a requested pod, then remove the reservation. So this is the entire component diagram of our device plugin. So device plugin here, there are worker nodes, and this device plugin runs on each node with some additional sidecars like metrics exporter, and they are deployed by the operator, and operator can be deployed through the operator lifecycle manager. So cluster admin can set up the operator and device plugin by just clicking the install button. And the operator deploys the validator and custom scheduler. Okay, that's the current implementation. So as a last section, let me introduce the future design, DRA, or dynamic resource allocation. So DRA is the DRA that consists of API and the scheduler plugin specific code that DRA purpose. So the developer can create a specific driver for certain devices. For example, in our case, we can implement Spire DRA driver, and we can employ the existing device plugin to cluster-wide optimized device allocation. And we use this kind of extension to the existing device plugin. But in the DRA framework, we can specify structured parameters like this. So we don't need to, force expand the manifest of the ports. So DRA now and the future. So the DRA is now under, how to say, in the process of the designing and implementing. So now just now it is beta release, but it will be it will become stable in the next release, I believe in August. And many KEPs are in progress for the DRA. So that is the, how to say, the promising technology for allocating devices to the Kubernetes workloads. And the one example, we can request the memories of each device by explicitly request the memory situation. So such additional features are in progress. Okay.
Okay. Yeah. All right. So, that's the final chart. So we are. That's summary. We now establishing the whole bunch of the schedulers, device plugin, plus the future device plugin. Then to make sure that topology-aware allocations and without the conflict of the resources, right? So that is our stance, and we are making sure that it will be available. Right now, it's only available in the Red Hat or the project catalogs, but we will soon open source in this repository right after this conference, probably next week. And also we can show some demos, and if you want to take a look some site of how it works, and please visit our sponsor booth. I will show there some details more. So thank you. Okay, so we have 2 more minutes. Anyone have any questions so far? Don't be shy. Okay.
Thank you for the very interesting presentation. I'm Hiroki from LY Corporation. I'm curious about the I don't remember that, but the custom resource binding to the hardware information in each node. So this one. So I'm curious about this is showing that the current hardware static status, but I'm curious about is there any dynamic information in that custom resource? Then so the daemon set is monitoring that something, and when some accident was the state, so is there any dynamic status in that custom resource or any use case or yeah?
Okay, thank you for your question. So this is as you said, we have the 2 types of the field we have. So one is a static field. Spec itself is a very static information. Yeah. Right, and how many PCIs card in here, in this, in the topology data. At the same time, you can see the status, with your allocator status for the port and the reserved status. Plus, we haven't shown that this details too much here on the spec side, but we have already managed on some status of the health of the card. So that is meaning, so some cases the card will be bad or not, or good healthy or status. So we have to actively manage this healthy status even in this state. So it can be used for the scheduling side, right? It's not, this card is not healthy, we should avoid this card for the allocation, something like that. So those kind of stuff is managed inside of this state. Some of the metrics is already exports to the Prometheus, right? So some metrics, hardware counters, those kinds of stuff. We don't manage these things in here. So we only keep in this side of the information, plus healthy or unhealthy cloud status.
Sorry, just clarify that. So is there any other custom resource including the status or something, or
no.
this
Yes.
custom resource?
Just keep using this one. Only keep using this one. It's a kind of centralized resources for the locking and then reservations, something like that.
Let me check you into the GitHub. So thank you. Okay. That's it.
All right.
Run out of time.
Any other? Okay, that's finished. All right, thanks again.
Thank you.